Assalamu alaikum. Before we take our number system convergence skills to the next level and start playing with the convergence of binary to and from octal and hexadecimal, I would like to recall something from first lecture of this series, and I would strongly encourage you to watch that video so that you have a firm concept of what I'm about to tell you. Let's consider a decimal number 6346. This number represents a quantity equal to 6000 plus 300s plus 4 tens and 6 units. The thousands, the hundreds, the tens, etc. are powers of 10, as this is power 10 raised to power 3. This quantity represents 10 square. This represents power of tens, and this is tens raised to power 0, which equals to 1. Now these represents the powers of tens amplified by the positions of the coefficients. To be more exactly, I can write these as 6 10 plus 3 into 10 plus 4 into 10 plus 6 into 10. Now starting from the rightmost, this 10 will have power of 0, this 10 has a power of 1, this 10 has a power of 2, and this is 3. This number can be written as in this way. However, the convention is to write the coefficients and from their position deduce the necessary power of 10. Okay, we just write it as this way. This whole equation, actually this is 6000 plus 300 plus 4 tens plus 6 units, but we don't write these tens. Okay, we write only the coefficients, these coefficients only. 6, 3, 4, 6. Okay, so the binary system is a different number systems. The coefficients of binary number systems have only two possible values, that is of 0 and 1. Okay, these coefficients and binary number is multiplied by power of 2. 2 will have some power. Okay, let's say for example, the decimal equivalent of this binary number 1101 can be shown from the multiplications of these coefficients by the power of 2. So what I mean by this, that actually this 1 into 2 plus this 0 into 2 plus this 1 into 2 plus this 1 into 2. This 2 will get 0, this will 1, this will 2, and this will 3. Now this is equal to 8 plus 4 plus 0 and plus 1. So this is decimal equivalent of this binary number. Bearing this concept of only writing the coefficients, we will now move on to our main topics, that is octal and hexadecimal numbers. The convergence from and to binary, octal and hexadecimals plays an important role in the digital computer, and since 2 cube is equal to 8 and 2 raised to power 4 16, so each octal digits corresponds to 3 binary digits and each hexadecimal corresponds to 4 binary digits. First we will study binary to octal, and here we can easily understand its relation. So the convergence from binary to octal is easily accomplished by partitioning the binary number into a group of 3 digits, starting from the binary and then proceeding to the left and right. This can be easily illustrated by the example. Okay, so this is our first example, and we have to convert this binary 101110 to octal number. So we have to group this binary digits into a set of 3 starting from the right. But why a group of 3? You can easily see that why we have to make a group of 3, so you can easily see. Now writing this number 101110. To make a group, we can start from left. So this one and this. In first group we get 110, and in second group we got 101. And start of my lectures I told you that 6000 346. There is a hidden powers of tens. It has a 10 that has a power of 3. This 3 has 10 power of 2. This 4 has 10 power of 1. And this has 10 which has a power of 0. Similarly, these digits have something power of 2. This 0 has 2 which has a power of 0. This 1 has 2 which has a power of 1. And this one also have 2 which has a power of 2. And similarly, so now this is first digits of second group. This also have 2 which has a power of 0, and this 0 has also a 2 which has a power of 1, and this one has also 2 that has a power of 2. Now you can see that there is one thing common in this group and this group, that from this anything that has a power of 0, it will be equal to 1, and this has become 2, and this will become 2 2s are 4, okay, and this also 1, 2 and 4. So this will be common for all of these members of group. So we need to multiply these things. So we have to bear this thing in mind, that is these coefficients have hidden tens and their tens have some power. So we need to know that these coefficients represent something hidden. And now we know that it is 4 2 1. So let me write it again. So this 1 0 1 and the 1 1 0. This group and this group. Now this will 1 2 4 1 2 4. Okay. So this will multiply with this one. So I will get 4 plus this will 0 plus 1 into 1. 1, and this one will be 4 plus 2, and this will get us 0. So as a result, I will get 5 and I will get 6 from here. So this way I will combine the octal digits and it will get me 5 6, and this binary number is actually equal to 5 6 to base 8. Okay, now we have to convert 1101101 to octal. For this number, we have to group the binary digits into a set of 3 starting from the rightmost. So let me write it. I will get 101 and second will be 101 and 1. Since the leftmost group has only one digit of 1, adding a couple of leading 0 to it to make it a group of 3. This is first group, second group and third group. Now to convert each group to its octal equivalent, each group member will get multiplied with corresponding number of the weight sequence. And we have that weight sequence of 4 2 1 4 2 1 4 2 1. So here I will get 0 will get multiplied by 4 will give me 0, plus this 0 will also get me 0. Because of this 0, this 2 will turn out to be 0. So we have 0 and 1 and 1 1, and for this group 1 will get multiplied with 4, it will give me 4, plus due to this 0 this 2 will become 0, plus and 1 into 1 will get me 1, and for this group 1 into 4 will get me 4, plus 0 into 2 0, plus 1 1 5 5. So these are the octal numbers, and this number has octal equivalent of 1 5 5 to base 8. In this last example of binary to octal, we have to convert 1011001111.10111.11110000110. So this is the number and we have to convert it into octal. Let me repeat that the convergence from binary to octal is easily accomplished by partitioning the binary number into group of 3 digits each, starting from the binary point and proceeding to the left and then to the right. Okay, so what I mean, let me write this number. So we made the groups of 3 digits. This is these 3 in the next, starting from the rightmost. Actually we get started from this one, but I am indicating group. Okay, now these 0 1 1, this is one group. We always start from this binary point and then moving towards the right. This 0 0 1, yes, this is the third group. Then this 1 1 0. Again, since the leftmost group has only 2 digits, adding a leading 0 to it, okay, to make it a group of 3. Now to convert each group to its octal equivalent, each group member will get multiplied with corresponding number of the weight sequence, and we know that the weight sequence is 4 2 1, 4, 2, 1, 4, 2, 1. Now this 0 will get multiplied with this 4. As a result, it will be 0 plus 1 into 2 will get us 2 plus 0. And now the second one, because of these one, we will get 4 plus 2. And this one will be killed. And now for this group, we have only 1. For this group, we will have 4 plus 1 into 1, 1. We are actually leaving the zeros, not writing them over here. Because of this 0, 4 will be turned out to be 0, and these one will be multiplied with these 2 and 1. So 2 plus 1 point, and here 4 plus 2 plus 1. And because of this one, we will get only 4. Then nothing from here. And here 4 plus 2. Because of this 0, this will be 0. Now let's format to get its octal numbers. So this will be 2, 6, 1, 5, 3.740, and now writing, so this number has octal equivalent of 2, 6, 1, 5, 3.740, to base 8. Now it's time to do reverse what we have done so far, that we have to convert octal numbers into binary numbers. It's super easy. Let's do this. As this is the first example, and we have to find out 5, 6 to base 8, its equivalent binary number. To do so, we will write separately 5 and 6. Now we want to break it down to numbers what I call octal weight sequence. That is 4, 2, 1 for this, 5, 4, 2, 1, and for this as well, 4, 2, 1. Now to convert this 5 into a binary number, need to realize that 5 is the sum of 4 and 1. So because we are using 4 and 1, we are going to replace that with 1. We didn't use 2. So we are going to replace that with a 0. Now 6 is the sum of 4 and 2. Since we use 4 and 2, we are going to replace that with 1. We didn't use 1, so let's replace that with a 0. So 5, 6 to base 8 is equal to 1, 0, 1, 1, 1, 0 and binary number. This time we have to convert to 6153.7406 to base 8, and we have to convert this number into a binary number, that is to base 2. To express these numbers in a binary, we will separate these numbers first, that is 2, 6, 1, 5, 3, 7, 4, 0, 6. Now you want to break it down to octal weight sequence, that is 4, 2, 1 per each one. 4, 2, 1, 4, 2, 1 for this 6, and 4, 2, 1 for this 6. Now to convert this 2 into a binary, need to realize that this 2 is sum of only this number, that is omitted. Because we have to use only 2, we gonna to replace this 2 with a 1. We didn't use the other 2 digits. Now 6 is the sum of 4 and 2. Since we use the 4 and 2, we are going to replace this 4 and 2 with 1. We don't use this one, so we will replace it with 0. So it will get 1, 1 and 0. Now 1 is actually present over here. That's why we're going to use only this one, and this will be turned out to be 0. Is we are no more required these 2 digits, that is 4, 2. We don't need these ones, so it will get 0, 0, and we need this one. 5 is the sum of 4 and 1. Because we use 4 and 1, we are going to replace it with 1. We didn't use 2, so we are going to replace it with 0. As this 3 is the sum of 2 and 1, so we are using only 2 and 1, so we will replace it with 1. And as we didn't use 4, we will replace it with 0. 7 is actually sum of all these three numbers. Is 4 plus 2 will get us 6 plus 1. So we will use all of it and it will be replaced with 1. Now this 4 is actually present over here and we don't need to use these 2 and 1s. We need to replace this 4 with 1 and this 2 and 1 with 0. And as this is 0, so we don't need to use these numbers. So we have to replace it with 0, 0. And again, this 6 is actually sum of 4 and 2. So we are using this 4 and 2. So it will be replaced by 1. And as we don't need or we didn't use this 1, so it will get 0. Eventually, this number is actually equal to, we don't need this leading 0. So starting from here, and it will be equal to 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 1, 1, 0. This octal number has a binary equivalent equal to this number. If you want to verify whether it is true or not, so I'm telling you that just a moment ago I have converted this number into an octal, which answer was this one, and now I have converted this one to a binary which equal to its original form. You can check if you go back 5-6 minutes back in this video. It's time to perform an operation of binary to hexadecimal number conversion. As I explained and start up this class that 2 raised to the power 3 is equal to 8 and 2 raised to the power 4 corresponds to 16, and hexadecimal is actually numbers to base 16 and octal was number system to base 8. Each octal digit, as we have seen, corresponds to the 3 binary digits. That's why we were making a group of 3 binary digits. And now this hexadecimal, which is to base 16, corresponds to 4 binary digits. That is why we have to make a group of 4 binary digits whenever we have to perform an operation of conversion from binary numbers to hexadecimal number system. So for octal number system, we were making a group of 3 binary digits, and now for hexadecimal number system we have to make a group of 4 members. As you can see over here, one thing that is necessary to tell you is I told this one in first lecture of this video series that it is customary to borrow the needed R digits for the coefficients of decimal systems when the base of the number is less than 10. Now, as we are dealing with a base that is 16 and it is more than 10, that is why the letters of the alphabets are used to supplement the 10 decimal digits when the base of the number is greater than 10. For example, in this hexadecimal number, the first 10 digits are borrowed from the decimal number, that is from 0 to 9. These are 10 digits, and decimal number system use these numbers. The range of its coefficient will be from 0 to 16 minus 1 to 15. This is the range of the coefficients. So when we have to write 10, then what? From 0 to 9 is done, but for 10, 11, 12, 13, 14, and 15. So we will use alphabets. A capital for 10, for 11 it will be B, for 12 it will be C, D, E, and for 15 it will be F. Keep this in mind and let's move on to examples. To convert a number 101101111 to hexadecimal, to do so, as I told that we have to make a group of 4 members of binary digits to convert it into a hexadecimal number. So let's do this. So making a group of 4 binary numbers and they can start from the rightmost digits. Okay, so let me write these numbers like 1 0 1 1 0 1 1 1. So this is the least significant figure, or this is the rightmost digit. So we have to make a group of 4 members. So 1, 2, 3, 4. This is first group, and this one is second group. Now each one of these will be multiplied into its hexabyte sequence, that is 1, 2, 4, and 8. So 1, 2, 4, and 8. Now this will multiply with this 8, and it will get us 8. And because of this 0, 4 will turn out to be 0, plus 1 into 2 will get us 2, and 1 into 1 plus 1 into 1 will get us 1. Now for this group, as this 8 gonna multiply with 0, so it will get us 0, plus 4 into 1 will 4, 1 into 2 will get us 2, plus 1 into 1 will get us 1. Now let's add it, and here we will get 11, and here we will 2 plus 6, 7, so it's 7. Let's combine these hexadecimal numbers or coefficients, but this 11 and 11 is equal to A, B, C, D, E, and F. So A is equal to 10, 11, 12, 13, 14, 15. This 11 will be equal to B, and 7 will retain its place. This B7 is the hexadecimal equivalent of this number. Here we have a binary number, that is 10110000110111. It involves a point. As I have told you in first example, that the convergence from binary to hexadecimal is easily accomplished by partitioning the binary number into a group of these 4 digits, starting from the binary point and proceeding to the left, and then to the right. So first we have to make a group. To do so, I will write these numbers. So this is first group 1, 1, 0, 1, and then 0, 1, 1, 0, and then 0, 0, 1, 1, and the last group will be 0, 1. As we don't have any digits, so we have to add couple of leading zeros, make it a group of 4. And now at this point we have to start from this side, and then we have to move towards the right. To do so, this will be 1 group, first group, and then 0, 0, 0, zeros, and then 0, 1, 1, 0. I have written this table. This table will help us. Now to do so, I will assign its hexadecimal weighted sequence, that is 1 for this group, 2, 4, 8, and this for second group, 1, 2, 4, 8, and as well for this last group, that is 1, 2, 4, 8. This group as well, 8, 4, 2, 1, 8, 4, 2, 1. Now for this group, because of this 0, this 8 will give 0, and this 0 will also kill this 4. So only from this group we will get 1. This is 1, and because of this 0, this will also be killed. This one will also be killed. From this group I will get 1 into 8 will get me 8, plus 1 into 4 will get me 4. And because of these zeros, there is no need to write these 2 digits. It will be plus 0 plus 0. And now is because of this 0, it will be turned out to be 0. And we will get only 4 and 2 because of these ones. Leaving out these zeros, 4 plus 2. And for this group, I will get 8. Plus, because of this 0, there is no need to write this one. 1 and 2 will get us 2 plus 1. And now, because of this one, I will get, so all of these digits will be added. And this will turn out to be 0. And because of these zeros, this 8 will turn out to be 0. And 4 and 1 will get us 4. Plus 1 and 2 will get us 2. Now let's mark the point. and it is here, so it will be right here. Simplify this. From this we get 1, and for here it's equal to 12, this 6, this 11, this point, and this will get us 15, and this 0, and then 6. Now the numbers which are greater than 10, we have to replace with these alphabets. So 1, yes, it is good to go. 12 has C. Now 6 will be the 10's place, and then 11, which is B. 12, 15, which is F. 0 and 6. This number has a hexa equivalent of, that is to base 16, 1, 3, 6, B, point, F, 0, 6 to base 16. In this question, we have been asked that we have to convert hexadecimal number into a binary number, and the conversions from hexadecimal to binary is done by reverse of a procedure what we have done for binary to hexadecimal. Now each hexa digit is converted to its 4-digit binary equivalent, and let me explain this one. First, I will separate these two A hexadecimal coefficients to A, C, 5, and D. Now you want to break it down to these number, what I call hexadecimal weight sequence, that is of 8, or 2, 1, or this one also 8, 4, 2, 1 for this one, 8, 4, 2, 1 for this 5, 8, 4, 2, 1, and for the 8, 4, 2, 1. From this table, I can see that this A is actually equal to 10. So to make it obvious, this A is here to express a value of 10. This C is 12. And for this 5, we are using this one, and for this D is actually equal to what? To 13. To 13. Now as this is 2, so it is present in this sequence, so that's why we need to replace this 2 by 1, and as we are not using 8, 4 and 1, so replace it by 0. Now this A, which is equal to 10, and this 10 is the sum of 8 and 2. So we are using 8 and 2, and that's why we will replace this 8 and 2 by 1. And as we are not using 4 and 1, that's why replaced by 0. Now this C, which is equal to 12, that's why 12 is the sum of 8 and 4. So we are using 8 and 4, replace it by 1. And as we are not using 2 and 1, so replace it by 0. This 5, and as 5 is the sum of 4 and 1, that's why we are using 4 and 1, so replace it by 1. And as we didn't use 8 and 2, so replace it by 0, 0. And this D represents a value of 13. 13 is the sum of 8, 4 and 1. As we are using 8, 4 and 1, so replace it by 1. And we didn't use this 2, so replace it by 0. So this number has a binary equivalent of 1, starting from the 1 as leaving out the leading zeros. So 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1. But wait a minute, as we have point before D, so let's spot that one. As we have point before D, so it's here, and D it's here, means it's here. So we have to spot a point, it's here, okay? Binary numbers are difficult to work with because they require 3 or 4 times as many digits as their decimal equivalent. What does this statement say? Is actually highlighting a challenge in working with binary numbers. Binary numbers are longer compared to their decimal equivalent. for every digits in binary number, it may take 3 to 4 times as many digits to represent the same value in decimal form. For example, the binary number 1111 12 ones is equal to 4095. Despite the challenge, digital computers work using binary numbers. There are situations where human needs to communicate directly with computers using binary numbers. To address this challenge, a strategy is introduced. It involves maintaining the binary numbers within the computers while reducing the complexity for humans. This is achieved by connecting the binary systems with the octal or hexadecimal systems. In this approach, human thinks in terms of octal or hexadecimal numbers instead of binary. When communication with the machine requires binary, human converts between the systems using visual inspection. This number has octal equivalent of 7, 7, 7, and 7. So this binary number has octal equivalent of 777, which has 4 digits, and when this number is converted to hexadecimal, it becomes F, F, and F, 3 digits. So when people discuss binary numbers and computer context using octal or hexadecimal presentation is more efficient. It requires fewer digits, about a third or a quarter, compared to equivalent binary presentations. When human interacts with machines, they convert between octal, hexadecimal, and binary using a visual inspection. So this is applicable when communicating with machines where switches, lights are machine language programs. So this video actually got a bit longer. Don't forget to subscribe my channel and also hit the like button. So see you in next video. Thank you.